Now, this is very much similar to, let's suppose in classical mechanics, if I want to solve a mechanics related problem, I start with the Newton's second law, F is equal to ma. And then from there onwards, I can simplify, I can make certain calculations to get values of certain variables. Or in the context of Lagrangian formulation, we start with the Euler-Lagrange equation. So every theory, even in, let's suppose, special theory of relativity, we have the Lorentz transformations, etc. So all these theories have certain postulates, certain basic axioms associated with it. And quantum mechanics may, you can say that Schrodinger equation is one of that kind of a fundamental equation. कि कोई भी quantum mechanical system अगर हमें study करना पड़े, if we want to study a quantum mechanical system, we start with the Schrodinger equation. So the Schrodinger equation goes something like this, and I'm going to first write down the time dependent Schrodinger equation version. So the most general form of the equation is the time dependent Schrodinger equation. But later on, what we can do is many times the we can separate the time dependence part from the space dependent part, and then we simply need to solve the time independent Schrodinger equation and combine it with the time evolution function separately at the end of it. ठीक है, but थोड़ा सा हम इसको ऐसे just let's start here. So this is nothing but a 1D version of the time independent Schrodinger equation. And because it's 1D, therefore here you see the second order partial derivative with respect to x. अगर आपके पास 3D होता तो this would become d2 upon dx2 plus d2 upon dy2 plus d2 upon dz2. ठीक है? If you want to study this problem in 3 dimensions, but in a different coordinate system, let's suppose a spherical coordinate system, then you just have to take the sort of a transformation of this Laplacian in spherical coordinates. Here I have written it in Cartesian coordinates, which is the most simplest looking expression. Spherical coordinates may it has a different form in terms of r theta phi. Especially this is important for hydrogen atom. Of course, you are familiar with the different kinds of quantities involved here. So for example, we are dealing with a potential here. The potentials that we deal with mostly are time independent. So here we have taken a potential which is only dependent on x. You are dealing with the constants, you have iota, you have h cross, and on the right hand side you have the time dependent part. Anyways, this is the starting point of quantum mechanics as a theory. This gives us an expression that we can work on. This gives us an equation that we can try to solve. And then further, we can do analysis of a system. Now, the first question that arises is that if I really want to start solving a problem in quantum mechanics, let's suppose I do end up solving this equation, even though it's a very hard equation because it involves partial derivatives with respect to both x and time, and even most standard quantum mechanical problems, the derivations are quite lengthy. But even if we are able to solve it, then what would the final result look like? So the solution that this Schrodinger equation actually ends up giving is what we call as psi. Okay. So because the equation here is a time dependent Schrodinger equation, therefore psi is a function of x and t. Of course, in 3D, this x would simply be r. Okay. But this is known as the wave function solution. Now, the wave function solution is a solution of both position coordinates as well as time coordinates. हम क्या करते हैं? Most of the time, we want to separate the sort of functional relationship between a psi or an eigenfunction with respect to position and phi, which is the time dependent part with respect to time. ठीक है? But उसमें आने से पहले सबसे पहले तो ये है कि what does this signify? Okay, and this is where the Bond statistical interpretation arises. So Bond statistical interpretation is an addition to the Schrodinger equation. Okay, it does not follow as a result of the Schrodinger equation because the Schrodinger equation doesn't tell us what the wave function is. The Schrodinger equation simply gives us a mathematical solution, which is the wave function. At max, it can tell us the evolution of the wave function with respect to time. But it doesn't tell us how to interpret this wave function solution. उसके लिए there we need an additional sort of a, a condition, which is the Bond statistical interpretation, which simply says that this basically wave function solution, since it's a complex function, right? Here we have a differential equation that contains iota, right? The differential equation contains iota, and therefore the solutions are complex in nature. Therefore, at the very beginning, we come to realize that this is not any physical quantity like energy, force, acceleration, velocity, position. So we deal with physical quantities in physics. But unfortunately, in quantum mechanics, the solution does not represent a physical quantity. And that is one of the sources of the struggle when you are dealing with quantum mechanical theory. Because we are not dealing with physical quantities as such, but we are dealing with something that contains within it some information that about a physical system that we can find out if we perform certain mathematical operations. So for example, the first thing that we can know is the probability density. So for example, if you have some kind of a wave function solution with respect to x, and you plot this wave function solution with respect to x mod square, then this simply gives us an idea about the probability density associated with a measurement to find the particle in a given system, uh, in a given region. Okay, यहाँ पे we are taking in terms of at a particular point in x. So the probability density is given by psi x comma t mod square, and because it's a complex function, this can be written as psi complex conjugate times psi. So this gives us an idea about the variation of the probability density. So at the very beginning, it introduces to us a probabilistic nature of quantum mechanical theory. That quantum mechanics cannot give us a direct information as to where the particle exactly is, but it can give us a probabilistic interpretation that if I make a measurement, it's likely that the particle might be here, but in a different measurement, the particle might be somewhere here. In another measurement, the particle might be somewhere here. In another measurement, particle might be here. In another measurement, particle might be here. It's another measurement, particle might be here. In another measurement, particle might be here. It's like throwing a dice. You cannot predict if you throw a dice कि क्या आने वाला है 1 2 3 4 5 6 कुछ भी आ सकता है. But you do have a probability as to मुझे what is the probability of getting 1 or what is the probability of getting 2, something like that. Same thing we have in quantum mechanical theory also. And because it's the probability density, if I want to find out the probability of finding a particle in a given region, then that is simply given as, let's suppose I want to find out what is the probability of finding the particle between, let's suppose x is equal to a and x is equal to b. ठीक है, x is equal to a यहाँ पे हो गया, x is equal to b यहाँ पे हो गया. That is simply coming from the area under the curve. ठीक है, so PAB is simply nothing but you integrate psi mod square with respect to position from x is equal to a to x is equal to b. This is the Bond statistical interpretation. Now, this directly leads to something called normalization, because probability has a meaningful uh, information, right? When we talk about probability, it cannot just take any random value. So, for example, probability cannot be -1. Probability cannot be 100. Probability has to be something that exists between 1 and 0. Right. So what is the probability that if I toss a coin, मुझे heads मिलने वाला है? It's either 0.5 or something. something in that range. Like theoretically it's 0.5 if I perform a large number of calculations, जिसको हम 50% बोलते हैं. But it's not 10, it's not minus 20, something like that. So the moment bond statistical interpretation comes into the picture, we have something that is purely an external condition that arises that we need to impose on the quantum mechanical system. And this is basically normalization. Whenever we deal with quantum mechanical solutions, they have to be normalized. Otherwise, they will not give us meaningful information. What it means is that if I perform the calculation of probability of a wave function solution from minus infinity to plus infinity, that means what is the probability that the particle exists somewhere in the universe in the one dimension, then it has to be equal to 1. It cannot be more than 1. It cannot be less than 1. This is a must. This is like some condition that we have to impose. तो ऐसा हो सकता है कि एक डिफरेंशियल इक्वेशन का जो एक सोल्यूशन है वो अलग अलग टाइप के सॉल्यूशंस हो सकते हैं. सो फॉर एग्जांपल, if I have a differential equation like d2y upon dx2 plus y is equal to 0. Right, this is perfectly fine. Now, what is one type of solution for this? We can have some oscillatory solution, sin x plus cos x. मैं बोल सकता हूँ, let's suppose I have sin x as a solution here. So I can also say 2 sin x is also a solution here. Multiplying with a constant doesn't really make much of a difference, right? So in a mathematical sense, multiplying the solution function with a constant doesn't make any difference. But it does make a difference in quantum mechanics because this is a condition that we impose externally speaking. तो इसका मतलब ये है कि अगर कोई भी वेव फंक्शन सॉल्यूशन हमें मिलता है, we have to ensure that it is normalized. Okay, so how do you normalize it? Normalization करने के लिए कुछ नहीं करना पड़ता. You simply, let's suppose, say that there is a normalization constant, and that normalization constant is equal to 1 upon integration of psi star psi dx root over. ठीक है ना? This is the normalization constant. Fine. तो सबसे पहले the first thing that you end up realizing is that it is not enough for a solution to be the solution of the Schrodinger equation. You also have to have it normalized so that it makes sense as to calculations of probability density. But this thing doesn't really just stop here. ये यहीं पे खत्म नहीं होता है. There are other conditions that we have to impose on the wave function so that it represents an acceptable solution for a given system. तो इसके ऊपर भी काफी सारे क्वेश्चंस पॉसिबल है. सो व्हाट आर द कंडीशंस? necessary for acceptable wave function solutions. आप बता सकते हैं? What do you think? You can write in the chat. What are some of the conditions which is necessary for wave function solutions to be acceptable so that we do not reject it? बहुत बार ऐसा होता है that we have to reject solutions because they are not acceptable because they don't satisfy some criteria. So what are those criteria apart from the fact that it has to be normalized or it has to be normalizable at least? बताइए. You can write in the chat also. Otherwise, you can switch on the audio and come on. It's a very easy question. I'm sure you know. Ram Kiran should be finite. Correct. It should be finite because infinite अगर wave function हो गया तो probability density will not make any sense also. What about other quantity? Any other condition? बताइए. Come on. These are very basic questions. What are other conditions apart from the fact that the wave function has to be finite? Finite इसलिए होना पड़ेगा because if it is infinite, then the probability density will also become infinite, which again doesn't make any sense. How can the probability of a particle being found at a given point is infinite? It cannot. So it has to be finite. Perfect. Anything else apart from finite? Wave function and its derivatives should be finite, single valued, and continuous. Yes, correct, Tanya. So wave function has to be finite because, as I said, its probability has to be less than 1 in a given region. It has to be single valued because if it is more than single valued, if it is multi-valued, it simply means that the wave function has multiple values at a given point, जो हो नहीं सकता. How can a particle have multiple probabilities of existing in the same region? ऐसा नहीं होता. It has one value of probability. It has to be continuous. Why does it have to be continuous? Because its derivatives have to be finite. ठीक है? It has to be continuous because the derivatives cannot be infinite. और derivatives ज़रूरी क्यों है? Derivatives ज़रूरी इसलिए है because later on we will see the derivatives gives us some information about the momentum. And also, अगर आप श्रोडिंगर इक्वेशन को देखते हैं, श्रोडिंगर इक्वेशन इटसेल्फ कंटेन्स द सेकेंड ऑर्डर डेरिवेटिव. ठीक है? तो not only the first order derivative has to be finite, even the second order derivative has to be finite. Because if the second order derivative goes to infinity, any region, then the equation itself will not going to make sense. And any other property? Sumana, single valued continuous, correct. Ramkiran should be double differentiable. Yeah, exactly. So let me list these things. It's going to help in certain kinds of problem solving. So basically, बहुत ही simple चीज है. The wave function solution of the Schrodinger equation must be single valued so that there is one distinct probability density associated with the particle in a given region or at a given point, not more than one. More than one would not make sense. It should be finite so that the probability density is less than 1. It must be continuous so that the derivatives are not infinite. The derivatives correspond to momentum and the derivatives of the derivatives correspond to the particular term in the Schrodinger equation. So therefore, the continuity is important with first order derivatives. First order derivatives, and the first order derivatives must be finite, again, single valued, and continuous. It must be continuous so that the second order derivative doesn't become infinite. And of course, the wave functions must be square integrable so that we can normalize them. Square integrable matlab, if you look at this particular expression, here we are doing an integration of the mod square of the wave function. So if I have the wave function mod square and the integration here with respect to x from, let's suppose, minus infinity to plus infinity, this itself has to be finite. If it is finite, then we can always normalize it. Right? Normalization के लिए हमें कुछ नहीं करना पड़ता है. Normalization के लिए we just have to multiply with some constant. So if it is 100, we can make it 1 by multiplying with a constant. But if it is infinite, then that is not possible. Okay. So it cannot go to 0, then we cannot normalize it. It cannot go to infinity, then we cannot normalize it. So it has to be finite because being finite means that it is normalizable. Of course, there are some other conditions as well if you want to include them here. So for bound systems, if a particle is bound to some potential, it is obvious that the wave function must satisfy boundary conditions. Now, यहाँ पर थोड़े से कुछ exceptions आ जाते हैं. So we were talking about the first order derivatives being finite and whatnot. So for example, if I have a particle in a box or something like that, where V is equal to infinity at the walls, then at the walls itself, the wave function must be zero because the particle cannot penetrate. But here the derivatives are not necessarily zero. Okay, so the wave function has to be zero here, and it must satisfy boundary conditions, and psi goes to zero as, let's suppose, x or r for 3D cases tends towards plus minus infinity. Of course, wave function solutions cannot be oscillatory. Solutions cannot be oscillatory at plus minus infinity. Now, questions related to acceptable wave function solutions are uh, rare, but they are quite possible. ठीक है, TIFR या जेस्ट लेवल के एग्जाम्स में क्वेश्चंस थोड़े बहुत सिंपलर होते हैं, गेट में थोड़ा सा कॉम्प्लेक्स क्वेश्चन पॉसिबल है. लेट मी गिव यू एन एग्जांपल ऑफ अ क्वेश्चन दैट यू माइट गेट रिगार्डिंग दिस पर्टिकुलर टॉपिक इटसेल्फ. ठीक है, कोई अगर आपको क्वेश्चन में कोई वेव फंक्शन सॉल्यूशन दे दे या कुछ ऑप्शंस दे दें और पूछें कि which one of them has to be which one of them are physically acceptable, which one of them are sort of unacceptable, then you'll have to figure out. Sometimes the questions may involve mathematics, sometimes the questions may involve diagrammatic representations, but based on these conditions you will have to sort of select the correct option in that particular question. मैं आपको एक दो सवाल देता हूँ that will give you an idea of what we are talking about. So, all right. So this is a question from GATE 2024. थोड़ा सा इसमें एडिशनल कॉन्सेप्ट्स है, बट आई थिंक मोस्ट ऑफ यू गाइज आर परफेक्टली फाइन विथ इट. यहाँ पे एक डायग्रामेटिक क्वेश्चन है तो मैंने डाल दिया इसमें. ठीक है, इट बी बिकॉज रीसेंट क्वेश्चन है तो आई थिंक we should go through it once. A particle is subjected to a potential which is Vx is equal to infinity at x less than equal to 0 and V naught from A to B and 0 elsewhere. If A is greater than 0, B is greater than A. If the energy of the particle E is less than V naught, which one of the following schematics is valid quantum mechanical wave function for the system? So this question doesn't like exactly belong to this particular topic, but you can use this particular topic to solve this particular question. तो इस तरह के क्वेश्चंस पॉसिबल है जहां पे देयर माइट बी अ डायग्रामेटिक रिप्रेजेंटेशन ऑफ अ वेव फंक्शन और प्रोबेबिलिटी डेंसिटी इन सम सॉर्ट ऑफ अ पोटेंशियल लैंडस्केप, और फिर वो पूछ लेंगे कि कौन सा डायग्राम वैलिड है. तो यू कैन सॉर्ट ऑफ कंबाइन ऑल योर नॉलेज टू गेट द आंसर. इट्स अ वेरी इजी क्वेश्चन, रीसेंट क्वेश्चन है बट वेरी इजी. बताइए विच इज द करेक्ट आंसर टू दिस. Sumona, correct answer? Anyone else? गेट का सवाल है बट बहुत आसान है. पोटेंशियल लैंडस्केप कुछ ऐसा दिखता है. दिस गोज टू V इज इक्वल टू इन्फिनिटी. फिर बीच में आ जाता है यहाँ पे एक पोटेंशियल बैरियर. फिर सारा कुछ हो जाता है जीरो। दिस इज द पोटेंशियल लैंडस्केप। Which is the best diagrammatic representation? Come on. Ram Kiran, correct answer. Tanya, correct answer. Good. All right. So, how do we reach the correct answer here? सबसे पहले let's start from the left hand side. जहां पे v is equal to infinity, wave function क्या होना चाहिए? जहां पे v infinity होता है, wave function goes to zero. Because if you look at the Schrodinger equation, if v becomes infinite, the wave function solution will automatically become zero. So at v is equal to infinity, the wave function solution should be equal to zero, which is fine in options A, B and C. But option number D में नॉन जीरो है, तो ऑप्शन नंबर डी पॉसिबल नहीं है। अगर आप लेट सपोज जीरो से ए तक देखेंगे और बी जीरो से ए तक देखेंगे, तो मैं यहाँ पे ये लिख देता हूँ सी। सो बेसिकली एट जीरो व्हाट इज हैपनिंग? इनफाइनाइट वॉल, सो वेव फंक्शन शुड बी इक्वल टू जीरो। और अगर हम जीरो से लेकर के ए तक देखेंगे, देन दिस रिप्रेजेंट्स व्हाट? दिस रिप्रेजेंट्स ए हाफ इनफाइनाइट एंड हाफ finite sort of a particle in a box. It's a particle in a box, but not in a particle in a finite box or an infinite box, but rather particle in a box with one finite and one infinite wall. एक तरीके से it's like a particle in a one side is infinite and the other side is finite well. तो ऐसे situations में क्या होता है? ऐसे situations में you end up getting oscillations, which is what you are getting. है ना, ये oscillation आपको मिल गया। Perfectly fine, no issues. Oscillation जीरो तक नहीं जा रहा because the right hand side wall is finite. No problem. So you end up getting oscillations. So you are getting oscillations. The next is from A to B. A to B में क्या होता है? A to B is basically tunneling is happening. Tunneling क्यों होता है? E is less than V naught. जो tunneling solution होता है, it is always exponential decay. Tunneling solution is always an exponential decay. टनलिंग में एक्सपोनेंशियल डीके ही एक सॉल्यूशन मिलता है। सो दैट मींस दिस ऑप्शन इज नॉट पॉसिबल, ए इज नॉट पॉसिबल, सी इज ऑल्सो नॉट पॉसिबल। ए में क्या हो रहा है? देयर इज अ बंप। सी में क्या हो रहा है? देयर इज एन ऑसिलेशन। बोथ आर नॉट पॉसिबल। द ओनली एक्सपोनेंशियल डीके दैट यू कैन सी इज बेसिकली फॉर ऑप्शन नंबर बी। और अगर आप एक तो ये जीरो में देख लिया, फिर जीरो से ए में देख लिया, फिर ए टू बी में देख लिया, एंड फर्दर ग्रेटर देन बी अगर आप देखोगे, दैट इज जस्ट अ फ्री पार्टिकल। फ्री पार्टिकल का जो सॉल्यूशन होता है वो ऑसिलेटरी होता है। अगेन, अगर आपको थोड़ा इसमें कंफ्यूजन लग रहा है, आई विल बी डिस्कसिंग सम ऑफ दीज टॉपिक्स अगेन व्हेन आई एम टॉकिंग अबाउट 1D पोटेंशियल्स। उसमें हम थोड़ा स्टेप पोटेंशियल क्वांटम टनलिंग को फिर से डिस्कस करेंगे। सो इफ देयर इज एनी कंफ्यूजन, it will become clear then. So if we combine all of these things, the only option that makes sense is option number B. Answer B is the correct option. ठीक है? सो पोटेंशियल इनफाइनाइट है, उस टाइम पे आपको जीरो वेव फंक्शन मिलेगा। फर्दर जीरो से ए तक पार्टिकल इन अ बॉक्स है, हाफ वॉल इज इनफाइनाइट, हाफ वॉल इज फाइनाइट, तो इस तरह का एक कोई ऑसिलेटरी सोल्यूशन मिल रहा है आपको। ठीक है, बट राइट हैंड साइड में वो जीरो तक नहीं जा रहा है बिकॉज इट्स अ फाइनाइट वॉल। बट बिकॉज ई इज लेस देन वी नॉट, एज इट पेनेट्रेट्स दिस रेक्टेंगुलर बैरियर, यू सी एक्सपोनेंशियल डीके। ठीक है, but the moment it exits the rectangular barrier, you see another free particle oscillatory solution. That's it. Very simple. Done. Okay, चलिए आगे बढ़ते हैं। आई होप द क्वेश्चन इज क्लियर टू एवरीबडी। नाउ थोड़ा स्पेसिफिकली जो हम वेव फंक्शन प्रॉपर्टीज डिस्कस कर रहे हैं उससे रिलेटेड मैं एक सवाल देता हूँ। जस्ट गिव मी अ मोमेंट। Okay, another question from Gate Physics. Which of the following allowed wave function for a particle is an allowed wave function for a particle in a bound state? And the options given to you are options for sort of not a graphical representation, but mathematical functions. बताइए. You are given wave function solutions as mathematical expressions. How can you figure out which one of them represents an acceptable solution for a bound state? बताइए इसका आंसर क्या होगा. Done. All right. Tanya, correct answer. Ram Kiran, correct answer. Priyanka and Sumona, correct answer. Very good. Excellent. All right. So, जल्दी से इसको कर देते हैं. So, mathematically, we have to figure out whether it satisfies the conditions that we have written earlier. Wave function must be finite, single valued. Derivatives must be finite, single valued. Wave function must be continuous. वो सब चीज़ें हमें यहाँ से चेक करना पड़ेगा. कैसे कर सकते हैं? Let's take a look at each mathematical function. So, for example, अगर हम पहले फंक्शन को देखते हैं, what does it look like? Does it look like the function has a singularity here? Of course. अगर मैं r is equal to 0 पुट करूंगा तो the wave function automatically becomes infinite. ठीक है, और it tends to infinity. as r tends to 0, which is kind of obvious. So this is not finite. Therefore, first option reject. सेकेंड ऑप्शन अगर हम देखें तो सेकेंड ऑप्शन में क्या होगा? अगर r इज इक्वल टू जीरो होगा, देन द वेव फंक्शन इज इक्वल टू r इज इक्वल टू, अगर जीरो है, इज जस्ट n, इट्स फाइनाइट, नो इश्यूज. और अगर r आपका इन्फिनिटी होगा, लेट्स सपोज r टेंस टू इन्फिनिटी होगा, तो वेव फंक्शन विल बिकम अगेन सेम. और अगर आपका जीरो होगा, अच्छा नहीं सॉरी, ये जीरो हो जाएगा, वन माइनस वन इज जीरो. एंड आर अगर आपका इन्फिनिटी होगा तो वन माइनस जीरो एन हो जाएगा, विच इज ऑल्सो फाइन. और अगर आर नेगेटिव इन्फिनिटी होगा तब दिक्कत होगा, दैट वेव फंक्शन नेगेटिव इन्फिनिटी होगा तो this is going to tend to negative infinity again. So this is not finite. And again, as I said, that for a bound system, the wave function must go to zero as x or r tends to positive negative infinity. So that is also not happening. So wave function is not possible. लास्ट वाला ऑप्शन एक देख लेते हैं, बहुत सिंपल है. लास्ट वाला ऑप्शन, दैट इफ यू हैव दिस काइंड ऑफ अ वेव फंक्शन जहाँ पे you plot with respect to r and you plot with respect to psi, then it is non-zero for r less than r, है ना. r less than r अगर यहाँ पे हम कर लेते हैं r less than कैपिटल R, तो ये है आपका. एंड इट इज जीरो फॉर r ग्रेटर देन r यहाँ पे, तो ये क्या हो गया? दिस इज डिसकॉन्टिन्यूअस. डिसकॉन्टिन्यूअस होगा तो डेरिवेटिव्स विल ब्लो अप. देयरफॉर दिस इज ऑल्सो नॉट पॉसिबल. ऑप्शन सी ही रहता है, बट ऑप्शन सी में हम अगर थोड़ा सा एनालिसिस करें तो हमें क्या मिलेगा? इफ वी एनालाइज ऑप्शन सी, सो हियर अगेन r इज इक्वल टू अगर जीरो होगा तो देन द वेव फंक्शन विल कम आउट टू बी जीरो. r इज इक्वल टू जीरो, एक्स स्क्वायर प्लस वाई स्क्वायर प्लस जेड स्क्वायर को हम आर स्क्वायर लिख सकते हैं. सो दिस इज इक्वल टू एन ई टू द पावर माइनस एल्फा आर ई टू द पावर माइनस बीटा आर स्क्वायर, ऐसे लिख सकते हैं. ठीक है. सो r इज इक्वल टू जीरो, सो बेसिकली दिस इज जस्ट इक्वल टू n. एंड इफ r टेंड्स टू लेट्स सपोज पॉजिटिव इन्फिनिटी होगा तो ए फंक्शन इज गोइंग टू टेंड टू जीरो. एंड इफ r टेंड्स टू negative infinity, then wave function will tend to what? नेगेटिव इन्फिनिटी में क्या होगा? नेगेटिव इन्फिनिटी में दिस इज n e टू द पावर माइनस एल्फा आर e टू द पावर माइनस बीटा आर स्क्वायर. नेगेटिव इन्फिनिटी पे e टू द पावर इन्फिनिटी और e टू द पावर इन्फिनिटी हो जाएगा ना. देयर आर टू थिंग्स दैट आर गोइंग टू हैपन हियर. नेगेटिव इन्फिनिटी में दिस इज गोइंग टू टेंड टूवर्ड्स infinity and this is going to tend towards 0. So what is going to happen? There are two exponential terms. बताइए. Exponential to the power minus r will tend towards infinity and exponential to the power minus r square will tend towards 0, because if r is negative infinity, r square will be positive infinity, right? So what is going to happen overall? Any guesses? What is going to happen overall here? इसको आप ऐसे सोच सकते हैं that which one function will dominate here. And of course, e to the power minus beta r square function will dominate over e to the power minus alpha r function. Why? Because r square है, right? जैसे जैसे r नेगेटिव इन्फिनिटी की तरफ बढ़ेगा, this term will become a very large number and this term will become a very small number, but it will become so small because of the r square term present in the power that the product itself is going to go to zero. ठीक है. The product of these two terms is going to go to zero. सो परफेक्टली फाइन, दिस इज द करेक्ट आंसर। ठीक है, आई होप इट मेक सेंस। आंसर इज ऑप्शन नंबर सी। चलिए, सो डायग्रामेटिकली आपसे पूछा जा सकता है कि व्हाट आर एक्सेप्टेबल वेव फंक्शंस। मैथमेटिकली भी आपसे पूछा जा सकता है कि व्हाट आर certain mathematical wave functions which are acceptable to us. Now, moving on to the next topic. I said initially that the very first question that arises when you look at the Schrodinger equation is what sort of meaningful information can we derive from the Schrodinger equation, है ना? क्योंकि इसका जो सॉल्यूशन है वो कोई रियल क्वांटिटी नहीं होता है, तो what sort of meaningful information can we actually get from the Schrodinger equation? And in that context, we talked about the Born statistical interpretation and how we can get an idea about the probability density of a particular particle's position. लेकिन there are some additional things we can find out. अगर हमें पार्टिकल के पोजीशन की अगर हमें पार्टिकल के पोजीशन की प्रोबेबिलिटी डेंसिटी मिल जाती है या प्रोबेबिलिटी डिस्ट्रीब्यूशन मिल जाता है, we can also, because of we are familiar with statistics, we can also find out the average position of the particle, है ना? We can also find out the most probable position of the particle, and furthermore, by sort of doing certain calculations using the Schrodinger equation, we can also find out the average momentum of the particle. Okay, because the particle also has some velocity associated with it, so it has some momentum. So that falls under what is called expectation values. Right. Now this is purely a mathematical framework. मैथमेटिकल फ्रेमवर्क है ये। क्यों? क्योंकि मान लेते कि हमारे क्लास में 10 बच्चे हैं और सबका जो है मैं हाइट मेजर करता हूँ। somebody is 5 foot, somebody is 5'5", somebody is 5'10", and I create some sort of a distribution. तो आई गिव यू द डिस्ट्रीब्यूशन कि ये पूरे क्लास में 10 बच्चों का ये हाइट का डिस्ट्रीब्यूशन है। तो based on mathematical theory, purely mathematical theory, you can easily calculate the average height in the class, right? You can easily calculate the average height in the class. Similarly, अगर marks का distribution दे दूँ, तो you can calculate the average marks in the class. The expectation value is nothing other than average. So when we calculate the average of a quantity, we call it expectation value. Okay, and it is simply done for various physical parameters. So let's suppose we talk about position. The easiest way to understand is you take the wave function complex conjugate, you sandwich the position and again the wave function function, and then you integrate from minus infinity to plus infinity, and this will give you the average position of the entire system. So that means, जैसे कि मैंने स्टार्टिंग में बताया था, that if I make a measurement of a particle's position in a given quantum mechanical system, हो सकता है कि one measurement it is somewhere here. If I make another measurement, it is somewhere here. If I make another measurement, it is somewhere here. If I make another measurement, it is somewhere here. We can calculate the average of all these measurements, and that will give us some information about the entire system itself. So for example, if you are familiar with the hydrogen orbitals, है ना, हाइड्रोजन ऑर्बिटल्स का जो पिक्चर होता है वो क्या होता है? इट्स नथिंग बट दिस, because if you try to measure the position of an electron in a hydrogen atom repeatedly in similar systems, then it might be in different positions. But the hydrogen orbital is simply the probabilistic representation of all these measurements. And we are more of the time, most of the time we are interested in the average position. So this is the average position. और ये तभी होता है when let's suppose the wave function is normalized. Because normalization becomes very important, right? So if wave function is not normalized, if psi is नॉट नॉर्मलाइज्ड, मैंने यहाँ पे क्या लिखा था, हाँ नॉर्मलाइजेशन कांस्टेंट ये आ गया, तो फिर दिस इज सिंपली रिप्रेजेंटेड बाय अ मच मोर जनरल एक्सप्रेशन कि यू टेक द एवरेज ऑफ पोजीशन and then you multiply with the normalization constant square, which is psi star psi dx. ठीक है, जब भी आपको कोई डाउट है whether a wave function is normalized or not, then you can use this in the denominator. It will automatically be normalized. In fact, it's always a good idea whenever you start a problem solving exercise of calculating something, that you first check if the wave function is normalized or not, and then you proceed further. Okay. Similarly, if I want to find out any kind of a function, let's suppose this is a sort of a standard technique of finding out the average of various functions. So for example, if I want to find out something like x square का अगर मुझे एवरेज निकालना है, तो मुझे बस ये करना है that instead of x, I'll simply substitute x square here in the sort of a sandwich expression, and I'll get the average of x square. If I want to find out any kind of a function of x and its average in this quantum mechanical system, so instead of this x, I'll just sandwich fx psi star psi ke beech mein, and I integrate it. And this will give us the answer. And similarly, you can take this process forward and calculate something for, let's suppose, momentum. ठीक है? Momentum क्या होता है? Momentum is nothing but the time derivative of sort of the position times mass. So for example, हमें पता है that P is basically equal to mv in classical mechanics. ठीक है? अब यहां पर हम v जब बोल रहे हैं, what is v per se? We don't really know what v actually is, but we can have some sort of a general idea. For example, if you look at the evolution of a system, let's suppose कि कोई quantum mechanical system में I measure the probability density distribution of a given system at a given point in time. Fine. फिर थोड़ी देर बाद, एक घंटे बाद, एक सेकेंड बाद, I again measure or I again try to calculate the probability density distribution for the same system, और तब हमें मिलता है कि that system has moved forward like this. हो सकता है systems evolve with time. So initially the probability density, let's suppose at uh, time t is equal to 0 is here, and the probability density at some other time t is here. Now what we can say is that we can look at what is the average position initially. So let's suppose the average position initially is here. This is x. And what is the average position at a later point in time? Let's suppose it is here at a later point in time. Okay? Then we can associate a sort of a velocity expression of this particular motion. समझ रहे हो? So we are looking at the time derivative of the average position of the particle. So we are looking at the time derivative of the expectation value of position. So here, if I am interested in finding out, let's suppose the expectation value of momentum, what we do is so this is m dx upon dt. We simply do, this is m d expectation value of x upon dt. That's it. X हमें already मालूम है. You just have to find out the derivative. So if you follow this procedure, what do you actually end up getting? You actually end up getting something like m d upon dt. You know the expectation value of position, which is x psi star x psi dx, right? Now, of course, this represents a derivation that you can check in any standard textbook like Griffith's, where you use the Schrodinger equation to simplify this expression. And when you do, you end up getting this particular expression, that P is simply equal to minus iota h cross from minus infinity to plus infinity. You end up getting psi star d psi upon dx. Okay? This is the expression you get. So this is the expression for the expectation value of momentum, which can also be written in a much more different manner. So you can write it like as if you are sandwiching a particular term, which is nothing but minus iota h cross del upon del x. So you have, इसको मैं del लिख देता हूँ, psi dx. ठीक है? Now, why am I writing it in this particular manner? Because this represents a technique of figuring out the expectation values of any kind of a physical quantity. which is you sandwich something called the operator which is associated with that particular quantity. This is known as the operator of momentum, as opposed to x, which is known as the operator of position. याद है मैंने स्टार्टिंग में ही कहा था that we cannot figure out direct physical quantities in the quantum mechanical theory. Instead, we get something called a wave function, which is a complex function, and you have to perform certain mathematical operations on the wave function to reveal some information about a physical quantity. And that is the structure of the quantum mechanical theory. अगर आपको पोजीशन का एवरेज चाहिए तो यू परफॉर्म दिस एक्सप्रेशन. अगर आपको मोमेंटम का एवरेज चाहिए you perform this particular expression. In fact, if you want to find out any other quantity, for example, if you want to find out the expectation value of kinetic energy, then you write the expression for the operator of kinetic energy and you sandwich it in this particular manner, you will get the answer. So expression for kinetic energy क्या होता है? So मैं साइड में लिख देता हूँ. तो पोजीशन का हो गया आपका x, मोमेंटम का आपका हो गया माइनस आयोटा एच क्रॉस डेल अपॉन डेल एक्स. काइनेटिक एनर्जी का आपका हो जाएगा काइनेटिक एनर्जी इज इक्वल टू पी स्क्वायर अपॉन एम. सो हियर आई कैन टेक पी स्क्वायर, आयोटा आयोटा स्क्वायर, आयोटा माइनस कैंसिल हो जाएगा. सो माइनस हो ये हो जाएगा आपका माइनस चला जाएगा, सॉरी माइनस आ जाएगा यहाँ पे माइनस एच क्रॉस स्क्वायर अपॉन टू एम डी टू अपॉन डी एक्स टू. ये आ गया. तो इसको ऐसे लिख सकते हैं दैट यू हैव साई स्टार माइनस एच क्रॉस स्क्वायर अपॉन टू एम d2 upon dx2 psi dx integrate from minus infinity to plus infinity. Similarly, total energy का भी आप कर सकते हो. You can take any kind of a, if you want to find out total energy, you can take any kind of a physical quantity, convert it into its operator expression, sandwich it between psi star and psi and integrate, you will get the expectation or the average value of that particular quantity. नाउ इसमें एक एडिशनल चीज मैं और बता देता हूं दैट वंस यू आर कंफर्टेबल डीलिंग विथ एवरेजेस ऑफ वेरियस क्वांटिटीज, you should also be able to do questions that involve uncertainties associated with those quantities. ठीक है. आपको याद है that we talked about uncertainties previously. Uncertainties सही है ना ये? Yeah, I think I should say. So for example, if you want to find out the uncertainty of x, it simply is nothing but the expectation value of x square minus the square of the expectation value of x root over. ठीक है. You want to find out the expectation value of momentum, that is just uncertainty of momentum, that is just the expectation value of p square minus the square of the expectation value of p root over. ठीक है. And then there are certain kinds of questions which rely on this particular uh, expression. Let me give you a question, guys. इजी क्वेश्चन दूं या मुश्किल से मुश्किल सवाल दूं आप लोगों को? पहले एक इजी सवाल देता हूं मैं, है ना. एक्सपेक्टेशन वैल्यू कर रहे हैं तो लेट मी फर्स्ट गिव यू एन इजी क्वेश्चन. लेट्स ट्राई दिस. So this is a relatively easy question. या मतलब इतना इजी क्वेश्चन तो नहीं आएगा, बट जस्ट फॉर द सेक ऑफ प्रैक्टिस आई एम गिविंग यू, देयर इज अ वेव फंक्शन दैट इज इन वन डायमेंशन व्हिच इज गिवन बाय दिस, व्हाट इज द एक्सपेक्टेशन वैल्यू ऑफ पोजीशन। एक बार ट्राई करके देखो जस्ट फॉर द सेक ऑफ प्रैक्टिस। Let me check the answers. Priyanka, correct answer. Ramkiran, correct answer. Tanya, correct answer. Sumana, correct answer. Fine, good. It's a very easy question. ठीक है, I'm not going to solve this because it's a relatively easy. आप लोगों ने कर भी लिया है. In the PDF, I'm going to share the detailed solution. थोड़ा सा आगे बढ़ते हैं. Let me give you a little bit more maybe difficult question. Let me check. Hmm. All right. So this is a little bit more lengthier problem because it is going to ask you the uncertainty in momentum. ठीक है. So थोड़ी देर पहले मैंने आपको बताया था that you might get questions related to calculating uncertainties as well. And how do you calculate the uncertainty associated with an operator? In general, if you have any operator, let's suppose A, and you want to find out the uncertainty associated with A, then for that quantum state, you find out the expectation value of A square and the expectation value of A square it and square root of this. This is coming from statistics, okay? And then you get the uncertainty associated with that particular operator. So here they are asking you for momentum. So they have given you a normalized wave function and they are asking you find out the uncertainty associated with momentum. एक बार ट्राई करके देखो. See if you can solve it. Should we start? Yeah, should I wait for some time? Tanya, your answer is correct. Good. मैं स्टार्ट कर देता हूँ, ठीक है? So you have to calculate the uncertainty in momentum. So the uncertainty in momentum is given in this manner. So that means we have to first calculate p square and we also have to calculate p. तो ये दोनों हमें कैलकुलेट करने की ज़रूरत है. नाउ यहाँ पे हम कुछ चीज़ें यूज़ कर सकते हैं. सो फॉर एग्जांपल साई एक्स इज गिवन टू यू एंड साई एक्स जहाँ पे नॉन ज़ीरो है हम उसी को यूज़ करते हैं. सो √15 अपॉन 4a⁴ 5/2 a² - x² for -a(xa). All right. So let's start with the expectation value of momentum first. ये कितना आएगा? Has anybody calculated this? Has anybody calculated this? Minus iota h cross कितना आएगा ये? Psi star d psi upon dx integration with respect to x. Has anybody calculated what this is? Tanya, yes, you're correct. Ramkiran, correct. Sumana, correct answer. या एक्सपेक्टेशन वैल्यू ऑफ मोमेंटम इज जीरो. आप चाहे तो इसको कैलकुलेट कर सकते हो, बट यहाँ पे हम ये भी यूज़ कर सकते हैं कि फॉर एग्जांपल मैंने आपको स्टार्टिंग में ही बताया था दैट द एक्सपेक्टेशन वैल्यू ऑफ मोमेंटम इज नथिंग बट दिस पर्टिकुलर क्वांटिटी, है ना? सो द एक्सपेक्टेशन वैल्यू ऑफ मोमेंटम इज व्हाट? Expectation value of momentum is m time derivative with respect to time derivative of expectation value of x. Now if you look at the wave function that is given here, the wave function is time independent, and as a result the expectation value of position is also going to be time independent, right? It's interesting, it's like a shortcut. So the wave function is time independent, so the expectation value of position is time independent, and as a result the time derivative of a function which is time independent is zero. राइट, टाइम डेरिवेटिव ऑफ अ फंक्शन विच इज टाइम इंडिपेंडेंट इज जीरो. ठीक है, तो आप इसको डायरेक्टली जीरो लिख सकते हैं या फिर आप चाहे तो इसको कैलकुलेट भी करके देख सकते हैं, इसमें कोई वो नहीं है. माइनस आयोटा एच क्रॉस एंड साई की जगह पे यहाँ पे आ जाएगा 15 टाइम्स 15 अपॉन you'll have 16 a⁵ integration of a² - x² d by dx, and here you have a² - x² dx with respect to minus infinity plus infinity. So if you want you can calculate it, but मैंने आपको logic बता दिया है that if the wave function is given to you just as a function of position, then the expectation value of position will come out to be a constant of time, and as a result the time derivative will come out to be zero. So this should go to zero. Okay. Now the second term is a little bit interesting because this is not going to go to zero. Okay. So this is simply going to be equal to integration of psi star minus iota h cross d del upon del x twice psi dx, है ना? ये जो एक्सप्रेशन है थोड़ा सा ही कॉम्प्लिकेटेड हो सकता है. सो दिस इज माइनस and here you'll have just an x h cross square term and psi star, and then here you have d upon d लिख देता हूँ, doesn't matter, single valued function है. d2 upon dx2 of psi dx here, and this essentially ends up becoming minus h cross square times you have 15 upon 16 a to the power 5. Here you have a square minus x square, and d2 upon dx2 a minus a square minus x square with respect to x. तो इसको कैलकुलेट करने की कोशिश करते हैं. इट शुड कम आउट टू बी माइनस 15h क्रॉस स्क्वायर अपॉन 16 a to the power 5. And here you have d by dx of minus 2x. यहाँ पे हमें प्राइम लेना चाहिए बट कोई बात नहीं. Minus 15h cross square upon 16 a to the power 5. And this becomes minus minus plus 2. यहाँ से यहाँ पे हो जाएगा आपका 8 and d by dx of x a square minus x square dx. ठीक है. So this comes out to be 15h cross square upon 8 a to the power 5, and this is nothing but a square x going from. अच्छा, है माइनस इन्फिनिटी ज़रूरत नहीं है ना, बिकॉज दिस इज ओनली वैलिड फॉर माइनस ए टू प्लस ए. तो वैलिड फॉर माइनस ए टू प्लस ए, तो हम यहाँ पे माइनस ए टू प्लस ए लिख सकते हैं. सो वैलिड फॉर minus a to plus a, so minus a to plus a, minus a to plus a, and minus you have x cubed by 3 minus a to plus a. So therefore this expression so this is a square, and here you have a minus minus a, so this is 2a, and this is nothing but a cube, a cube by 3 minus plus a cube by 3, so 2a cube by 3, which is 2a cube minus 2a cube by 3. थ्री माइनस टू वन बाई थ्री. ओके, तो यहाँ पे 3 से हो जाएगा ये 5, 2 से हो जाएगा ये 4, ए क्यूब हो जाएगा ये स्क्वायर, एंड द आंसर इज 5h क्रॉस स्क्वायर अपॉन 4a square. Is this correct? 5h cross square upon 4a square. Or maybe I'm making a mistake somewhere. 2 minus 2 by 3. 2 कॉमन आ गया ना, सो 3 minus 1 2 हो जाएगा यहाँ पे, सॉरी 2 हो जाएगा. तो दिस इज गोइंग टू बिकम 2. ये हो गया 2, and this is the expectation value of p square. So therefore, finally, we can calculate the uncertainty associated with p, which is nothing but 5h cross square upon 2a square root over, therefore root 5 upon 2h cross upon a. This is the answer. Root 5h cross upon root 2a. This is the answer. Okay. So more or less it was straightforward in the sense that you just had to calculate the expectation value of momentum, and you had to calculate the expectation value of momentum square, and then you had to use the final expression to get the actual uncertainty. एक और सवाल मैं आप लोगों को देता हूं. Just stick with me. One more question. एक जेस्ट का क्वेश्चन है, थोड़ा सा इंटरेस्टिंग है, वो मैं आपको दे देता हूँ. Let us try this question. क्वेश्चन नहीं मिला मुझे। चेक। Yep. Yeah. All right. So this is a question from JEST, and this is also relatively similar, but थोड़ा सा अलग है. Just for practice, you can sort of try. All right, here it is. So JEST 2020, the wave function of an electron in one dimension is given by this. What is the ratio of the expected position and the most probable position? ये दोनों टर्म्स जो है बहुत इंपॉर्टेंट है, बिकॉज अलग अलग क्वेश्चन में पूछा जा सकता है एंड समटाइम्स स्टूडेंट्स में गेट कंफ्यूज कि दोनों टर्म्स का मीनिंग क्या है. सो एक्सपेक्टेड पोजीशन मैंने आप लोगों को बता दिया है. एसेंशियली मीन्स टेक्निकली स्पीकिंग द एवरेज पोजीशन. और मोस्ट प्रोबेबल पोजीशन का मतलब क्या होता है? एनीबडी? व्हाट इज द मीनिंग ऑफ मोस्ट प्रोबेबल पोजीशन? द मोस्ट प्रोबेबल पोजीशन सिंपली मीन्स जहां पे प्रोबेबिलिटी डेंसिटी हैज ए मैक्सिमा. ठीक है, अगर मेरे पास एक इस तरह का प्रोबेबिलिटी डेंसिटी है, राइट, इस तरह का प्रोबेबिलिटी डेंसिटी है साई स्क्वायर, इसकी एक एवरेज क्वांटिटी होगी और इट हैज अ मिनिमा मैक्सिमा हियर. तो दिस विल रिप्रेजेंट, दो मैक्सिमा दे दिया मैंने बाय द वे, दिस विल रिप्रेजेंट एक्स एम, विच इज स्लाइटली डिफरेंट कंपेयर टू द एक्सपेक्टेशन वैल्यू. एक बार ट्राई करो, इनफैक्ट साथ में ट्राई करते हैं. ठीक है, एनीबडी नोज द आंसर? Where the probability of particles maximum? Yes, correct, Priyanka. Yep. So sometimes they might ask you expectation value. Sometimes they might ask you the most probable position. दोनों की meaning थोड़ी सी अलग है. They are not necessarily the same quantity. Okay, so psi x is given as 2 root 3, 2 root 3 e to the power minus x, 1 minus e to the power minus x. Okay, now we can calculate both these two quantities separately. तो मैं यहाँ पे एक लेफ्ट हैंड साइड राइट हैंड साइड में अलग अलग मेजर करने की कोशिश करता हूँ. सो फर्स्ट लेट अस ट्राई टू कैलकुलेट द मोस्ट प्रोबेबल दिस थिंग पोजीशन. मोस्ट probable position, and second let's try to calculate expected position. ठीक है, so most probable position we can find out where the probability has a maxima, where the probability distribution has a maxima. So what is the probability distribution? It is nothing but psi x mod square. Complex function तो है नहीं, तो this is going to be 3 into 4, 12 e to the power minus 2x, 1 minus e to the power minus x square, है ना? So therefore इसको हम क्या कर सकते हैं, you this. So we can take a derivative of this maxima find out करने के लिए. So dp upon dx at the most probable position is equal to 0. So this is dy dx of 12 e to the power minus 2x, 1 minus e to the power minus x square at xm is equal to 0. इसको सॉल्व करके कितना आ रहा है बताइए. सॉरी, इसको सॉल्व करके कितना आ रहा है? ये बन जाएगा e⁻⁴x और e⁻�3x, है ना? आई थिंक सो। डेरिवेटिव लेने से पहले तो ये बन जाएगा आपका -2 e⁻⁻2x -4 e⁻⁴x माइनस माइनस प्लस 3 into 2 6 e⁻⁻3x is equal to 0। सो इसको अगर हम कॉमन ले लेंगे e⁻⁻2x -2 -4 e⁻⁻2x प्लस 6 e⁻⁻x इज इक्वल टू 0, है ना? तो यहाँ पे x ग्रेटर देन इक्वल टू 0 पे ये मैक्सिमा हो नहीं सकता, बिकॉज e⁻0 लगा देंगे तो 1 हो जाएगा, है ना? तो इसको हटा देते हैं एंड दिस बिकम्स हैज एनीबडी कैलकुलेटेड दिस? थिंक आई एम मिसिंग समथिंग हियर, बट मैं एक बार दोबारा से करके देखता हूँ। आई एम गेटिंग some mistake, I guess. So 3 into 4 is 12 e⁻⁻2x and 1 minus e⁻⁻x square। ये है probability density। फाइन, यहाँ पे क्या करें हम? यहाँ पे इसको इंडिविजुअल नहीं करते। आई थिंक इट्स पॉसिबल दैट आई मेड सम मिस्टेक। इंडिविजुअल नहीं करते, इसी को यूज करते हैं एज अ प्रोडक्ट ऑफ फंक्शंस। दिस इज 12 वैनिश हो जाएगा। दिस इज 1 minus e⁻⁻x square, and then -2 e⁻⁻2x is one term। श्योर हो रहा है बहुत ज्यादा। 12, 1 minus 0 minus x square minus 2 e to minus 2x, ठीक है, and plus 2 1 minus e to the minus x square or e to the minus 2x is equal to 0. 12 vanish, so this is minus 2 e to the minus 2x 1 minus e to the minus x square plus 2 e to the minus 2x 1 minus e to the minus x, नहीं यहाँ स्क्वायर नहीं होगा, सॉरी, 2 1 minus 2 minus. This is minus minus plus and e to the power minus x. Fine. Okay. I'm sorry, yaar. I'm getting distracted because there is a lot of noise going on outside my house and थोड़ा distraction हो रहा है उसकी वजह से. And this is minus 2 e to the minus 2x 1 minus e to the minus x square plus 2 1 minus e to the minus x और यहाँ पे आ जाएगा e to the minus 2x minus 3x आ जाएगा यहाँ पे minus 3x is equal to 0. So therefore this is equal to 2 vanishes and you're left with e to the power minus 2x 1 minus e to the minus x square is equal to minus 3x 1 minus e to the minus x. So again this vanishes, e to minus 2x यहाँ पे हो जाएगा e to the minus x and therefore this is nothing but 1 minus e to the minus x is equal to e to the minus x and therefore 1 minus e to the minus x minus e to the, या फिर I should say 1 is equal to 2 e to the minus x. All right, finally stuck हो गया था, I'm sorry. So e to the power minus x is equal to half or xm is equal to log of half. ठीक है, that's it, log of half. So log of half is the this thing. Now similarly we can also find out the expectation value. Expectation value is del x is equal to, यहाँ पे आएगा आपका साइज mod square x dx. तो psi mod square is nothing but 12 e to the power minus 2x 1 minus 0 minus x square x dx. Has anybody calculated this yet? ये भी थोड़ा सा लंबा हो जाएगा. कैलकुलेट किया है किसी ने? प्रियंका 0.69, हाँ करेक्ट है प्रियंका, मतलब एग्जाम इज करेक्ट. रामकिरण हैज कैलकुलेट द फाइनल आंसर. फाइनल आंसर इज नॉट करेक्ट आई थिंक. प्रियंका गोरियन योर फाइनल आंसर इज करेक्ट, या फाइनल आंसर इज करेक्ट बट इसको सॉल्व करना है. सो सॉल्विंग requires that I simplify all these terms. So let's simplify all these terms. 12 integration e to the power minus 2x. So this is 1 plus e to the power minus 2x minus 2 e to the power minus x x dx. So this is equal to 12 integration of, so this is x e to the power minus 2x dx. एक ये टर्म आ जाएगा, है ना, एक ये टर्म आ जाएगा एंड दूसरा आएगा आपका x e to the power माइनस 4x, ये एक टर्म आ जाएगा, x e to the power माइनस 4x और एक आ जाएगा माइनस 2 x e to the power minus 3x. सो ये एक इंटीग्रेशन हो गया, और -2, ये एक इंटीग्रेशन हो गया, दिस इज विद रेस्पेक्ट टू डी एक्स, विद रेस्पेक्ट टू डी एक्स। फाइन, तो यहाँ पे हम क्या कर सकते हैं, यहाँ पे हम वी कैन यूज स्टैंडर्ड इंटीग्रल्स, राइट। स्टैंडर्ड इंटीग्रल हम लगा सकते हैं। सो फॉर एग्जांपल, ये जो रीजन है, रीजन इज फ्रॉम जीरो अपवर्ड्स, तो ये बेसिकली जीरो से ऊपर हो गया, जीरो टू इन्फिनिटी वाला रीजन है, जीरो टू इन्फिनिटी वाला रीजन है। सो देयर फॉर दिस बिकम्स, मैं डायरेक्ट स्टैंडर्ड इंटीग्रल्स का ही वैल्यू लिख देता हूँ आपको, ठीक है। जो स्टैंडर्ड इंटीग्रल फॉर एक्स e⁻²x dx from 0 to infinity, that will basically uh, come out to be 1 by 4, and the standard integral from 0 to infinity x e⁻⁴x dx, that will come out to be 1 by 9, and from 0 to infinity x e⁻�3x, that will come out to be, sorry, x e⁻�3x will come out to be, x e⁻�3x will come out to be 1 by 9, and x e⁻⁴x will come out to be 1 by 16. Okay, I'll leave the standard integrals up to you, and इसको मिला करके जो आंसर हमें आता है, दैट कम्स आउट टू बी 12, और यहाँ पे आ गया आपका 1/4 प्लस 1/16 माइनस 1/4 प्लस 1/16 माइनस 2/9। ठीक है, आई थिंक दिस इज करेक्ट, राइट। 12 इंटू 1/4 प्लस 12 into 1/16 minus 24 upon 9, and this comes out to be 13/12। ओके, मैं डायरेक्ट आंसर लिख रहा हूँ, अभी ज़्यादा टाइम नहीं है हमारे पास। 13/12, एंड फाइनली द रेशियो जो हमें चाहिए था, द रेशियो इज एक्सपेक्टेड पोजीशन और प्रोबेबल पोजीशन के बीच, एक्सपेक्टेड पोजीशन और प्रोबेबल पोजीशन के बीच। सो एक्सपेक्टेड पोजीशन इज 13/12 and probable position is log of half. The answer comes out to be around 1.56 के अराउंड आता है। This is the answer. Anyways, very sorry I got a little distracted. बहुत ज़्यादा यहाँ पे noise हो रहा था, and this noise really distracts me. बट अदरवाइज इट्स नॉट रियली दैट डिफिकल्ट। मेरे को थोड़ा ज़्यादा टाइम लग गया है इंटीग्रेशन के साथ, बट अदरवाइज इट्स नॉट रियली दैट डिफिकल्ट। द कॉन्सेप्ट इज, ज़्यादातर क्वेश्चंस में एक्सपेक्टेशन वैल्यू ऑफ पोजीशन पूछते हैं, कुछ क्वेश्चंस में प्रोबेबिलिटी मैक्सिमा वही पूछ सकते हैं, मोस्ट प्रोबेबल पोजीशन, रेशियो वगैरह या कुछ समथिंग सिमिलर ऐसा पूछा जा सकता है। एंड इफ यू कंबाइन ऑल दीज इन्फॉर्मेशन यू विल गेट द फाइनल आंसर। Yeah, Ram Kiran, you also got the correct answer finally. Priyanka also got the correct answer. ठीक है, आई होप दिस इज क्लियर एवरीवन। थोड़ा सा मतलब ज़्यादा मुझे आज पढ़ाना था, बट नहीं हो पाया, कोई बात नहीं। एक्सपेक्टेशन वैल्यूज हमने आज डिस्कस कर लिया, एंड प्रोबेबिलिटी डेंसिटी और वेव फंक्शन फिजिकली एक्सेप्टेबल कब होता है वो डिस्कस कर लिया। अगले क्लास में वी विल अगेन स्टिक टू श्रोडिंगर इक्वेशन, बट वी विल डिस्कस द टाइम इंडिपेंडेंट श्रोडिंगर इक्वेशन। So there are questions based on just the time independent Schrodinger equation, expectation values of energy, as well as how to find out, अगर पोटेंशियल दिया रहेगा तो एनर्जी आइगन वैल्यू फाइंड आउट करना होता है, कुछ हाइपोथेटिकल पोटेंशियल्स का, वो उस तरह के क्वेश्चंस। या फिर कुछ क्वेश्चंस ऐसे भी होते हैं कि टाइम एवोल्यूशन के बारे में भी पूछते हैं कि आफ्टर सम टाइम व्हाट इज गोइंग टू बी द फेज ऑफ द सोल्यूशन या वट एवर, उस तरह के क्वेश्चंस हम डिस्कस करेंगे अगले क्लास में। एंड सो प्रोबेबली दिस इज अप टू, मतलब अगर आप लेक्चर्स देखोगे, दिस इज फ्रॉम लेक्चर नंबर 4 to 6। तो अगले क्लास में कोई लेक्चर नंबर 7 to 8 के बीच डिस्कस करेंगे, और फिर हम क्वांटम मैकेनिकल फॉर्मलिज्म में चले जाएंगे। ठीक है, चलिए आज के लिए यही रैप अप करते हैं, बिकॉज यू हैव अनदर क्लास एट 7:30। I'll take leave if you don't have any kind of doubts.